All right, guys, we're going to try to do this. I have to try to remember how to work everything on this video thing. I haven't done one of these in a while, but I'm going to try to see what we can do and try to get these notes done for you. Yesterday we left off and we were talking about the different cells, like the Hadley cells, the Farrell cells, and the polar cells. We started out with a drawing that looked similar to this. So what's happening in that drawing is this convection process. Each of those 6 cells across the planet has hot air rising up. As it rises, it gets cooler and cooler and cooler. By the time it gets to the top, it's lost all of its moisture and it's cold. It lost its moisture because as air cools off, the volume kind of compresses in. As it compresses in, it squeezes out that moisture. The saturation point decreases, it can't hold on to as much water, and that water begins to fall as precipitation. As that cold air that's become more dense now starts to sink down towards the surface, it starts to heat up. As it heats back up, it rises up, and it keeps that convection current and convection cell moving around. So when we did the drawing that we did in class, we ended up with 6 of those convection cells across the planet. Now, depending on which class period you were in with me, we got either to this point or a little bit further. The next thing that we have is there's going to be constant winds that start to blow across the surface due to these convection cells. Because when we look at the convection, again, we have that hot air rising up. So it's hotter at the bottom, colder at the top. Because as the hot air rises up, it's cooling off. So it becomes less dense, starts to rise up, but then as it gets colder and higher in elevation, it becomes more dense. As it becomes more dense, it starts to sink down to the surface and warm back up. So we're going from cold to hot here again. So we're going to have cooling happening here and warming happening here. Now, what's happening at the surface is we're also going to get a horizontal component to the convection. We're going to have the air going from one side to the other, and it's going to be from the area of high pressure to the area of low pressure. Now, the reason why the pressure differences are happening is because now, as that air is rising, think about it like a bunch of papers or a bunch of books or whatever stacked up on top of something. So if this is the surface down here, and I have all of these stacks of wind, or stacks of air rather, going up on top of it, that's a pretty high pressure down below it. But as I start pulling these off and removing them, the more I remove and allow to rise up in the sky, the less pressure I have on it. So I end up with an area of low pressure where that hot air started to rise up. Down here, I have the cold air sinking, so I'm stacking up more and more of the air on top. As I'm stacking up more and more of the air on top, I have more mass on top of it, so it's exerting a greater pressure. That pressure then squeezes the air and starts to go towards the area of low pressure. So that gives me my horizontal component to my convection cell. At the top, the same thing's happening. Now I'm going to have high pressure over here, low pressure over here, because I have more and more air coming up from below, stacking up, pushing up harder and harder. That's going to give me my high pressure. Down here, I have stacks of air falling down and sinking into the surface. So I get low pressure. So I'm going to get a sideways component up here. What that's going to do is when I look at my convection, it's going to give me constant winds that are going to blow from where the cold air is at to where the hot air rises. So I'm going to get a pattern of winds that go in this pattern. And again, each hemisphere is just a mirror image of each other. So the south is the mirror of the north, and the north is the mirror to the south. Now, those convection cells create those winds. Those are our trade winds or our prevailing winds. They're always going to be blowing across the surface, and they're always going the same direction. However, they don't travel in straight lines. They don't travel in straight lines because we have the Earth is spinning. As the Earth rotates, it creates something called the Coriolis effect. So the Coriolis effect is that curvature of a straight path due to the spin of the Earth. So when I look back here, since the Earth is rotating, the object we're moving is going to be deflected. Since air still has mass, it doesn't have much, but it has mass. air has mass, so it's affected by gravity. So if I'm trying to move a mass of air in a straight line path downward, but my planet is spinning around that path, what happens is, as that mass of air is here, the gravity of the Earth is grabbing it and dragging it along with the spin of the Earth. And it creates kind of like a curved arc path. So my winds are never going to go in straight lines at the surface. They're going to kind of be curved and going off in an arc. So when I look at what happens at the different latitudes, again, I have my prevailing winds happening from 30 to 0. It should have been a straight line downward. Terrible color, hold on. So it should have been a straight line downward like this. That should have been the direction of my winds due to that convection cell that was going in this path. However, since the Earth is spinning, the Earth drags that air molecule along with it and deflects it off this way. So when I go back out here to this picture, instead of my arrows going straight up and down, you guys will need to change these and deflect them due to the Coriolis effect. So from 30 to 0, my winds deflect off to the west. Since they're originating in the east and deflecting to the west, we always name them for their point of origin. So these are going to be my northeasterly trades. Right? These will be my southeasterly trades. Right? Now up here again, it should go from north to south, or sorry, from south to north rather, but since I have the Earth spinning, it's going to deflect my winds off that way. They're originating in the west, blowing off towards to the east, so these are going to be my westerlies. Now with the westerlies, they don't differentiate between the north and the south. They simply call them the westerlies. So in the southern hemisphere, they're also the westerlies. At the poles, again, I have the same thing that's happening at the equator because it was the same original path of the air. Since it forms a pattern, I get this pattern of wind. These are the polar easterlies. And those are going to be my trade winds. Again, the deflection is caused by the Coriolis. The direction is caused by the convection cell. This is going to be the main important stuff that we talk about as we move on further. When we get into El Nino and when we talk about precipitation distribution and temperature distribution, it's all going to be fueled by these trade winds. So make sure that you guys know the things on this picture here. We're going to then use that and apply it to the rest of the chapter. When I get back in class tomorrow, we're going to do an activity to show that this actually happens. There's a way with spinning paper and drawing arrows to show and prove that that Coriolis effect is really happening, and it's not just me telling you, that something's occurring when it really isn't. So what you can do with this picture, this is basically what we just drew. You can take a picture of this, you can focus on it, whatever you want to do. Note that the blue arrows are from the polar cells, green arrows are from the Ferrel cells, red are from the Hadley cells. So they did a nice job with this picture and color-coded what winds are created from which convection cell. Right? And again, you have a bigger version of it and all of that. See, now the difference that they do here, we take it up to 30 degrees, they stop it at the tropics. Anywhere from that 23.5 up to 30 degrees, you're pretty fine with. But they stop those northeast trades right around the tropical zones. So really the Ferrel cell is going to be the largest of our cells. It's going to go up to around 60. So really it's from about 24 degrees up to 60 degrees, and then the Hadley cells are from 0 to 23. So this is going to be a smaller one. Polar cells are smaller. The Ferrel cells, again, are the largest. I didn't really care that you know that, as long as you know the trends that can apply those. College Board's never going to ask you exactly how big these cells are and things. All right, the next thing that's going to be affected by the wind patterns is something called the rain shadow. And the rain shadow is going to only occur on large mountains near the coast. So we need tall, high mountain peaks that are near coastal areas. So the Appalachian Mountains that we have in Pennsylvania, they're never going to have the rain shadow effect with them. They're not tall enough, and they don't have a water source nearby. We need that major source of major source of moisture rather, and we need that tall mountain range. So when we look at these ones, we're looking at mountains like the Andes Mountains, looking at mountains like the Himalayas. So those are the types of mountains that we're talking about. When we look off the coast of Oregon, there's the mountain range that runs through northern California, southern Oregon, all those ones. Those would have the rain shadow effect. But the ones that we have in Pennsylvania, we're never going to see the rain shadow effect. What's happening with it is we have two different sides of a mountain. We have the windward side, and we have the leeward side. I would definitely know those terms. The way that I always remember them, again, I'm the king of terrible analogies and crappy analogies. You guys remember the positive and the negative anions, onions, they smell, so you cover up and it's a negative charge. Terrible analogies. So when we look at the windward versus the leeward, the wind blows towards the windward side. The leeward side, the wind goes down the other side. It's like a roller coaster. When you're on a roller coaster and you're going down the hill, you scream leeward. So that's the way that it is. You're going towards the windward side, climbing up the mountain. As the roller coaster goes down the other side, you go wee, and that's the leeward side. All right. So the windward versus the leeward, those are going to play into what is happening. So we said we need a body of water, ocean, sea, something like that. That water is going to be evaporating and going up into the sky. All right, that evaporation creates warm, moist air. That warm, moist air gets pushed inward from those winds. As that warm, moist air gets pushed inland, it starts traveling up the mountain. So as the air hits the mountain, it deflects upwards and moves up. So I go from having warm, moist air to where it cools off. Just like when we talked about convection, as the hot air rose and became colder, my saturation point decreased. Since my saturation point decreased, I had lots of rain start to fall. Same thing's going to happen here. As the air cools, it takes it from being warm and moist, and we start having precipitation fall. It's going to be falling as rain at the bottom part of the mountain, and the higher up we get, it starts to fall as snow. And again, that will determine, based on seasons and things like that as well, what that elevation is. But again, we're going to have the wind and the snow. So we have an area of high precipitation on the windward side, and that high precipitation allows for abundant vegetative growth. So we get kind of like a split side of the mountain. If I'm looking at it kind of down along the mountain range, on the windward side of the mountain range, I would have vegetation all over the one side due to the increased rainfall happening as that warm, moist air gets pushed upward, cools off, saturation point decreases, and the water starts to fall out. By the time it gets to the top, it's going to be cold and dry. So going down the leeward side, I get that cold, dry air going downward. But the air starts to warm up, because now I'm decreasing my elevation. I'm starting to have that adiabatic warming start to happen. As I decrease my elevation, my pressure is increasing, and the adiabatic heating starts kicking in. So as the air warms, the saturation point also increases. What happens is that pulls moisture out of the ground. Not only do I have dry, arid conditions to begin with, but I'm drawing water from the soil. Because that air is looking for water anywhere it can find it. The very little bit of water that is in the soil gets pulled out and put into the air. As that happens, that creates a desert. So on these tall mountain ranges, we have a lush vegetative forest on the windward side. On the leeward side, I end up with a sparsely vegetated desert-like area. That's why they call that the rain shadow. We get rain on one side, the other side sort of like in a shadow where nothing is growing. And again, it's all due to those temperature changes causing different precipitation amounts. When you look at the next page in your notes, it does a good job kind of explaining this. I always like to draw the pictures a second time, but this is what's happening with that. They can do a lot better of a drawing than I can. So again, high evaporation with the prevailing winds coming in, that's going to be that warm, moist air. Warm, moist air going up the mountain cools off. As it cools, the saturation point decreases, we get increased precipitation. Lots of vegetation on the windward side, no vegetation on the leeward side, because now we end up with those warm, dry conditions on the leeward side. All right, and again, this is just the text of that. With the next part, now we're going to talk about how those wind patterns, the prevailing winds, are going to create ocean currents. The first thing that we end up with is something called a gyre or gyre. All right, what happens is when we have those prevailing winds blowing through the oceans, we end up with these land masses that kind of screw things up. So again, I'm such an artist. We have North America here, South America here, Central America here. If we look at where the equator runs, it's somewhere around in here. A tropical zone will kind of push us to here. So we should have these wind patterns going like this across this region. Because again, those are the prevailing winds. However, when those prevailing winds hit a landmass, it's going to deflect those wind patterns and create different ocean currents. So instead of them being able to go straight across, as the wind goes over the water, it's sort of like blowing on a hot bowl of soup or on a cup of coffee. The more you blow, the more it pushes that liquid forward, because there's that frictional force that drags it along with it. So in addition to the air currents, I also get my water currents following those wind paths. But as the water hits the continents and the water can't travel through the land masses, now it deflects them and it starts to hug around those land masses as it goes up. So now as these ones hit, now they're going to drag upwards and go this way too. What happens is we get these circular paths of water due to the way that the convection cells create those winds. And those circular paths of water are what the gyres are. There's going to be a few of those gyres across the map, and they're going to be pretty impactful for us from an environmental standpoint. So we have one here, one here, one here, one in here, one in here, and to a smaller extent in here. See if I can make this a little bit smaller. A little guy over here. All right, those gyres, they're going to be problematic for us because what's going to do, it's going to concentrate the ocean trash. We have a lot of plastic that ends up in the oceans because as the garbage trucks and things are driving, we have plastic that starts falling out of them. We put plastic in the environment because people are too lazy to throw things away and recycle them, so they throw it on the streets. You know, you're driving down the road, you have a plastic cup. Oh, I don't feel like waiting until I get to a garbage can, I'll just throw it out the window. All of that finds its way into the river systems. The rivers then bring that towards the ocean. When it dumps in the ocean, it collects in there. The ocean currents then start to circulate that, and we get the garbage patches across the planet. The Great Pacific Garbage Patch is so large now, it's over the size of Texas. So it would be the equivalent of taking up that much space on land. There's so much trash there that it's going to be almost impossible to clean it up. There's been some people out that have developed different ways to have bacteria eat the plastics away, sweep up the plastics. But the problem is when we take that plastic and sweep it up, we need to bring it inland then and put it in a landfill. So there's no good solution to the problem that we caused. We have to be aware of it in the future and reduce the amount of trash that we're putting into the oceans. And again, it's all about those gyres, those circular paths. Again, garbage patch, we'll talk about that when we're talking about pollution. Right now for the gyres though, you just need to know that it's anywhere where we have these circular paths. And again, you can see as the ocean current's moving across, it hits a landmass, gets pushed downward. That's what's creating these ocean currents. The ocean currents are what's going to distribute the temperature and precipitation across the planet. We can see that the United Kingdom is a much warmer temperature than what it should be at its latitude. If we look, it's at the same latitude as Scandinavia and Greenland. So it should be covered in snow and ice, but it's not. It's perpetually somewhere between that 30 degree and 80 degree temperatures all the time through the different seasons. The reason that is, this warm water that goes through the Gulf and through southern Atlantic Ocean starts getting picked up with the ocean currents. As it gets picked up, it blows across the Atlantic and starts coming northward, getting pulled by those trade winds. When we look at where it goes right off the coast of uh, United Kingdom. That's why the United Kingdom is always so rainy. It has a constant source of warm, moist air off its coast. It keeps the temperature a lot hotter. So as these cold currents come downward, they kind of mix with that warm current, creating fluctuations in the air temperatures. Lots of storms happen, all of those different things. So those are how the ocean currents are created. You guys should know the basics of it. You don't have to know the names of them, but you should know how the ocean currents are created. It's through the trade winds blowing across and how they deflect. They deflect as they hit the land masses, which curls them around. You should also know the gyres, and you should also know this stuff here, these upwelling zones. So right here is an upwelling zone, here, 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 and here. That's going to be important when we talk about El Nino. So keep the upwelling in the back of your mind right now. All right, there's a note on that. There's a note on thermohaline circulation. You guys can read all these and understand them, so I don't think we need to explain it. Make sure you're reading again what's on the right-hand side here, matching it up to the numbers in the chart. If you don't understand it, ask me next class period, and we'll go through it a little bit more in depth. All right, this here is where we're going to stop. I have a second video with this, and we'll go through El Nino in class. I want to make sure that I spend a little bit of time with you on it because it's a very, very important thing. It's going to be a weather phenomenon, not an actual weather storm, but it's going to be a phenomenon that happens. It's due to the reversal of the wind directions in that South Pacific. So in the South Pacific, where the winds usually are coming up this way, what happens during El Nino is they actually weaken and shift directions. That's going to flip-flop the weather that we experience, and it's going to affect 2/3 of the planet. So it is very, very impactful. Where it's usually dry, it's going to be extremely wet. Where it's usually wet, it's going to be extremely dry. So it's taking what the normal conditions are and really flipping and turning things on their head. So when we have an El Nino year, we tend to get killed with snow. Whenever California has an El Nino year, it tends to be really, really wet there. Where it used to be dry, now it turns really wet. That's going to have big impacts on the economy. It's going to have big impacts on everything. So we're going to spend a lot of time in class talking about El Nino, probably dedicate almost a whole class period to it. And that brings us really to the end. We talked about watersheds earlier in the year, so you guys hopefully should remember what those are and remember